Welcome to Signal Ahead. I'm Alfred. Today's briefing, Theory and Foundations, Physics plus Math. Sunday, July 19. This is the synthesis above the noise, not the headlines, but the deep currents beneath them. Let's get into it. There's a moment that ought to make anyone who follows science reporting pause. A week or so ago, a philosopher published a preprint with a wonderfully provocative title, something to the effect that the entire era of noisy quantum machines had been an 8-year trap, a parade of demonstrations the hardware was, as he put it, built to lose. The claim, stated boldly, is this: with one lonely exception, every flagship demonstration of so-called quantum advantage has, within roughly 18 months, been caught up with by classical computers running on ordinary hardware simulated, reproduced, or explained away. And the rebuttal, from one of the field's most careful voices, was equally sharp, that this narrative fundamentally misreads what was ever being claimed. Now here is the non-obvious thing, the connection a casual reader of the headlines would almost certainly miss. The interesting fact is not who is right about quantum computing. The interesting fact is that this is the same argument, wearing different clothes, that runs through nearly every corner of theoretical physics and mathematics right now. It is an argument about what counts as a result. When a classical algorithm catches up to a quantum experiment 18 months later, has the quantum experiment failed? Or has it done exactly its job, which was to draw a line in the sand and dare the rest of us to cross it, and thereby to teach us precisely where the frontier sits? The person who thinks a demonstration must remain forever unbeaten to have meant anything has misunderstood what a demonstration is for. A benchmark is not a monument, it is a provocation. And the whole health of a field can be read in how it treats its provocations, whether it sulks when they are beaten or learns. Hold that thought, because you will see it everywhere once you have the eye for it. Consider the quieter, stranger work happening at the foundations of particle physics, the long, patient effort to see whether the peculiar algebra of the octonions or the exotic structure known as a Jordan pair might encode the standard model's zoo of particles and forces. This is not experiment. Nobody is going to smash protons together next Tuesday to confirm a Jordan pair. It is a bet that the right mathematical language will make an ugly, arbitrary-looking set of facts suddenly look inevitable. That, too, is a provocation, a wager that beauty is a form of evidence, deferred. And it sits uneasily next to a very different mood elsewhere in the same discipline, the long-running, patient skepticism about whether certain grand unifying frameworks were ever science at all, or whether they were mathematics in a physicist's costume. Same field, opposite instincts about what a result even is. Then there is the humbler, almost domestic problem of how to marry two theories that don't want to speak to each other. The equations of electromagnetism, which respect the symmetries of relativity, and the equations of ordinary fluid flow, which respect the older Galilean symmetries. Slap them together, and you get, in the plain phrasing of the person working on it, a mess. And the response is not to declare one theory wrong, but to ask carefully what the correct low-speed limit of the fuller theory actually is, to take a limit properly rather than lazily. This is a recurring theme in the current state of the field. The interesting action is often not in some new fundamental law, but in the seams, in how you glue known theories together, in which limit you take, in what you keep, and what you throw away. And there is a third register entirely, which is about the tools we use to think. A great deal of energy right now is going into machine-assisted mathematics, coding agents that can, in an afternoon, build the interactive visualization of some subtle process that would once have cost a week of tedious programming. One of our most eminent working mathematicians has been candidly documenting this, the genuine liberation of it, and the trap inside the liberation, that these systems produce things which superficially resemble finished work long before they are actually correct, something that looks done and isn't. Which is, if you notice, precisely the same anxiety as the quantum benchmark debate, only pointed inward at our own instruments. How do you tell a real result from a convincing costume of one? So here is the argument I want to build over the next while. The state of theoretical physics and mathematics today is not best described by any single breakthrough, nor by any single crisis. It is best described by a discipline arguing, productively, with itself about the nature of evidence, about whether a beaten benchmark is a failure or a lesson, whether beauty counts, whether a limit is well taken, whether a machine-made picture can be trusted. These sound like separate quarrels. They are one quarrel. And in the segments ahead, I want to follow that single thread through the quantum question, through the foundational bets on octonions and unification, and finally through what our new automated tools are quietly doing to the very idea of understanding something. Stay with me. The frontier, it turns out, is a conversation. There's a paper that crossed my desk recently, a philosopher, working carefully through 8 years of quantum computing's proudest moments, arguing that every flagship demonstration of so-called quantum advantage has, within 18 months, been quietly reproduced on ordinary hardware, or shown to lean on some assumption it wasn't supposed to need. The hardware, the argument runs, was built to lose, designed in such a way that the victory it announced was never quite the victory claimed. It's a bracing thesis, and I want to sit with it, because it lets us hear the deep current running beneath all the noise of the field. Now the response from within the discipline was firm, that these demonstrations did not in fact fail. Both things can be true, and their both being true is precisely the point I want to make. What looks like failure, from a certain angle, is actually the ordinary metabolism of a science that is working. Consider what the 18-month clock really measures. A group announces that their device has done something no classical computer can feasibly match. And then, this is the crucial part, other people go and try. They sharpen their classical algorithms. They find the corner that was cut. They reproduce the result on a laptop, or they don't, and the claim survives. 18 months is not the half-life of a lie. It is the response time of a community that takes each other's claims seriously enough to attack them. The deep current, then, is not that quantum computing is a bubble or a triumph. It's that we are watching the boundary between the classically tractable and the classically intractable get mapped in real time by adversarial collaboration. Every demonstration that gets reproduced classically has taught us something precise about where the real frontier lies. It has moved the fence, not knocked it down. The single clear exception the philosopher grants, the one demonstration that hasn't been swallowed back into the tractable, is itself informative. Science does not advance by winning. It advances by discovering exactly how and where you were wrong and how fast. And this pattern of a frontier being probed, corrected, sharpened, you find it everywhere across the theoretical landscape right now once you tune your ear to it. Consider the humble business of taking a limit. Maxwell's equations respect one symmetry of spacetime. The equations of fluid flow respect a different, older one. Slap them together to describe a conducting plasma, and you get a mess, an incoherence at the seams. The interesting work is in the careful taking of a limit, the Galilean shadow of a relativistic theory, so that two frameworks built on incompatible foundations can be made to speak to each other without either one lying. That is the same current. Not the announcement of a grand unification, but the patient reconciliation at the boundary where two true things appear to contradict. Or take the long, stubborn effort to see the Standard Model, that baroque catalogue of particles and forces we verified to absurd precision, but never quite understood, reflected in some clean algebraic structure, the octonions, Jordan pairs, the exceptional objects that mathematics keeps producing as if in anticipation. 15 installments deep into that inquiry, and there is no victory lap. There is only the sense of a shape being felt out in the dark, a suspicion that the arbitrary is secretly necessary. Again, not conquest, but the slow correction of our ignorance about where the real structure sits. Even the sudden flood of visualization tools, these little interactive applets, spun up now in an afternoon by coding agents, letting one watch a random variable breathe or the zeta function unfold its process, even this belongs to the current, because the point being made about them is a point about correction. The prudent voice warns that these things produce something that superficially resembles a finished product well before it has been properly tested, which is exactly the 18-month clock again, compressed. The vibe-coded applet, the quantum supremacy claim, the unified field ansatz, each arrives looking done, and each must then survive the community's cold second look. So what is the structural trend beneath the noise? It's that theoretical physics and mathematics are not, at bottom, in the business of producing results. They are in the business of producing corrigible results, claims made precise enough and public enough that being wrong about them becomes possible and productive. The philosopher's charge that the hardware was built to lose assumes that losing is a scandal. But a discipline where nothing could lose, where every announcement stood unchallenged, would not be a science at all. It would be theology with better graphics. The current runs toward correction. It is slow, it is unglamorous, it is often mistaken in the short run for failure or hype, and it is the only thing that has ever reliably carried us toward the truth. When we return, I want to ask what happens to this current when the tools of correction themselves, the algorithms, the agents, begin to move faster than the humans doing the correcting. There's a small preprint that's been circulating, alleging something rather deflationary, that the entire 8-year run of so-called quantum advantage demonstrations was in essence rigged to fail, that with a single exception, every flagship result was, within 18 months, either reproduced on ordinary computers, shown to rest on questionable assumptions, or otherwise quietly walked back. The framing is that the hardware was built to lose. And I want to sit with what it would mean if that were true, and what it means that it largely isn't, because the distinction is where the real lesson lives. Here is the second-order point. A field can be both overhyped and genuinely progressing at the same time. Those two things are not in contradiction, though our public conversation treats them as if they were. When a classical algorithm catches up to a quantum demonstration 18 months later, the tempting story is that the quantum result was a fraud, but that is almost the opposite of what happened. The quantum result was a challenge, a line drawn in the sand that said, "We claim this is hard classically," and then hundreds of very clever people spent 18 months trying to erase that line. Sometimes they succeeded. That success is not the failure of the enterprise, it is the enterprise working exactly as it should. A demonstration that no one bothered to attack would tell you nothing. A demonstration that provokes a global sprint of classical algorithm design and survives some of it is telling you where the genuine frontier sits. So what should you watch for if you want to read this field honestly rather than emotionally? Watch the exceptions. When someone says every result but one was overturned, the interesting object in that sentence is the one. What made it durable? Which assumptions did it not lean on? The signal is never in the wreckage of the failed claims. It's in the residue that resists being explained away. Watch also for the shape of the classical rebuttals. There is a world of difference between showing that a quantum demonstration was simulable in principle and actually running the simulation on real hardware in comparable time. The word reproduced is doing enormous work, and it means different things to different people. A healthy skeptic and an overheated promoter can both be technically correct while describing opposite realities. Now I want to widen the lens, because this same tension runs through everything else crossing my desk this week, and it's the real subject here. Consider the quiet revolution happening in mathematical visualization, the sudden ease with which one can take a figure that already existed as code in a paper and turn it into a living, interactive applet. Something that used to cost weeks of tedious labor now costs an afternoon. And the honest observer of this notes the same trap in miniature. The process produces something that superficially resembles a finished product well before it has been properly tested. The prototype looks done. It is not done. That gap between the appearance of completion and the fact of it is exactly the gap between a headline quantum advantage claim and a claim that has survived 18 months of assault. This is, I'd argue, the defining epistemic hazard of our moment across the theoretical sciences. Our tools for generating impressive-looking results, whether physical demonstrations, coded visualizations, or machine-assisted arguments, have raced ahead of our tools for validating them. The favorable use case for these new methods is precisely the one where the downside of being wrong is small. A secondary visual aid, a teaching illustration, something non-mission critical. The moment you place weight on the output, the moment a result must bear the load of a genuine claim about the world, the standard of scrutiny has to rise, not fall, in proportion to how easy the result was to produce. And there's a deeper structural echo I can't resist naming. Think of the physicist trying to marry the theory of electromagnetism to the theory of ordinary fluid flow, one invariant under the transformations of relativity, the other under the older Galilean ones. Slap them together naively and you get a mess, because they answer to different symmetries. The resolution isn't to declare one theory a fraud, it's to find the careful limit in which they can coexist. That is the temperament this whole domain rewards. Not the breathless embrace, not the deflationary dismissal, but the patient work of asking, under what conditions does this claim actually hold, and where exactly does it break? So NISQ did not fail, and quantum supremacy did not fail, not in the way the sharpest version of the accusation demands. But the accusation is still doing something useful, because it forces the question of what durability means. What you should carry away is a disposition, not a verdict. When the next spectacular result arrives, quantum, mathematical, machine-assisted, whatever, resist the twin seductions. Don't buy the headline and don't buy its inversion either. Ask instead, what would it take to overturn this, and has anyone tried? The health of a field is measured not by how many claims it makes, but by how honestly it survives the attempt to unmake them. That's the signal for today. The noise will keep coming. We'll keep finding what's underneath it. This has been Signal Ahead with Alfred. Until next time.